breadth first search. It is one of the algorithm in graphs. So we'll just go through it. Here we have two references. I'll go with this one. So okay, first basically it's a fundamental transfer. It begins with a node. The important points about these are breadth. Breadth first search different from depth first search. That is, closest to vertices are restricted before others. B mainly transverses vertices level by level. Popular graphs algorithms are like Dikshitra's shortest path, Khan's algorithm, Prism's algorithm are based on BFS. This is very important when we are moving and learning more, and we'll discuss how they are based on these BFS. BFS itself used to detect cycles in a directed and undirected graphs, find the shortest path in the weighted graph, and many problems. It's important to know that where we have to use them and how this BFS is helpful in different types of problems or graphs. So here we have an example. So we can start, or we can take as a parent root with any of this. Okay. So wait, we can take any of this node. So this 0 is also 1. So 0 has 2 and 1 has it as its roots, and 3 is also. So in breadth first, what we do is, first we will go through 1 and we will dive into it. Okay, sorry, first we'll go to the first level. The first level is like 2 3 1, right? Then the second level is 4. In a depth search, what we do is in DFS, what we do is, we'll go on depth. So first we'll go like this: 0 2 4, then 0 3, then 0 1. Okay, in BFS we go something like 2 3 1, then we'll go to 4. In DFS, depth is like the one chain as long as it was, one chain as long as itself, For example, if 2 has 2 children, for example 3 has some 5 here, we'll go like 2 3 1, then 4 5. Okay, this is how the breadth first search is worked on. As I told, 0 2 3 1 4, 0 2 3 4. Okay, so another problem, if we can take anything as our node. I'm taking always my first preferences as a 0. We can go like anything. 0 is my first node, so the 3 children are these 2, like, okay, then first I'll go to 1. First we'll go to 0 to 1, then we'll go to 0 to 2, then 2 has 3 children, like 2 and 3, then this is the way. So the answer is 0 1 2 3 4, 0 1 2 3 4. This is the output. I hope you understand how I did this process. So how we make this happen, here. So BFS as a given source, algorithm starts at one given point, explores reachable vertices. So here we have, and how the algorithm, this is a basic concept. The before one I told is a basic concept. This one, what I'm telling is like the basic algorithm. Okay, we have here some thing 0 1 2, then we'll go 3 4, right? So this is what we see. Okay, we started at 0, so we'll get 0 here, as you see. So we'll get 0 and 0. And Q, what is a Q? We are not doing stack. Q is like LIFO, first in last out. First in last, first in first out. Okay, Q is like first in first out. So here we get 0, then we'll get 1, 2 in the visited boxes. So after the 1 is visited, we can't tell 1 is first visited, 2 is first returned. No, they are on the same level. So we'll write them as a scene, visited as the 0, 1, 2, and the queue is like queue is comes out in a queue. First in is first out. Okay, FIFI. I don't remember. So okay, sorry, FIFO. In queue, it's first in, first out. Okay, so this is how it works. Then what in the visited box will come? 0, 1, 2, 3, 4. Okay, let's see. Let's see. Okay, 0, 1, 2, 3. We can write 4 also. It's fine. Now the 1 is out. After that, the 2 will be out. Next 3 will be out, then 4 will be out. So here you see something called front in all the here. Front is like something that is going to be out, is its front. Okay, 2 is going to be out, then the 3 will be front. So this is how the algorithm works, and I'll try to explain this concept in coding part. Okay, here we have coding part, coding implementation of BFS Python. Here the steps is in a good English approach: installation, exploration, termination. We repeat the steps until the queue is empty. Okay, we'll see this code implementation BFS. So here. So first we get the collections, so that we whatever we want we'll get from the default dictionary. So here what we did is we created a graph, a class. So this helps us to this helps us to have the directed graph and using the adjacent list representations. So we created a constructor and we also created a default dictionary to store this graph. So I'll explain step by step. This is a normal constructor. Okay, then see self dot graph. I mean the constructor is holding the graph with the default dictionary in the list. Something like we are, whatever the graph has a numbers, we are holding something like a list in a normal way, like line wise. Okay, then we created a function to add an edge to the graph, like here add an edge. I mean here the edge is something called wait, so here the so we know these are vertices, and these are edges, right? So these are important how we travel. Okay, so basically we have two things, self u v. Okay, the graph u, once you get the u value u, then we'll append v. I mean append, adding something to end of the list. We call this as append. V is here in this example, if you get 0, then the second whatever the edge is connected, 1 will be appended in the next one, as I told you. So 0, 1, 2, it works on a loop, because it works on a loop. Okay, see here, and we started something like this will be used, it will be not used directly here, we will use them in the coming code. Okay, we are creating a function called BSF to print the graph. Self comma s here is something we can tell it's as a start. So s is something like a start. So once it is marked as visited, okay, if it is not marked as visited, okay, wait, mark all the vertices are not visited. Okay, yeah, until unless we visited, how can we tell it is visited or not visited? So first here we have a case of not visited. Visited is equals to false. Okay, keep that aside. How can we tell it is not visited? The maximum point, I mean for example we have 4 vertices. We count vertices from the point 0, 1, 2, 3. So max is 3, right? We added 1 because we started the indices from 0 to 3. So max is 3. We started from the 0, so we added +1 to the graph. Hey computer, take the max and its indices are end with max +1. The max is from the graph. So max of self dot graph is something that, hey computer, take the max from the computer. This is what we are actually telling. Okay, if it is we didn't visit if we didn't visit the max point, so tell that as a false. Next, creating a queue. Okay, we need to allow for BSF to do the programming part. Okay, we created a queue array here. Then we are telling here S is start. The S is start, right? See here. Wait a second. So the queue is created, start is 0 and this 0, here 0 will come in the first place, right? So we came 0. Okay, so visited. Okay, whenever the queue is appended, once you get the visited part and to get that into the queue part, then tell that it is visited as S. Once the queue is into the queue, once the S is into the queue part, then tell that it as a true. Okay, while queue is S is equals to q dot pop. Okay, we need to first in first out, right? We need to remove the last part until the queue is empty and all the visited has been filled. So here the code works on this property what I told. So S is equals to q dot pop of 0. Okay, until everything is done, pop it out. So okay, this is what okay, once it removes, just print the what left in the queue section. So here we have for I in the self of graph S. Okay, if not visited I, q dot append I visited equals to true. Okay, this is like getting the adjacent vertices of the dq vertex x. If an adjacent has not been visited, the mark it visited and nq it. If it is the adjacent is not, I didn't actually okay, then here is the so this part, this whole part explains the 0 is connected to 1, 0 is connected to 2, 0 is connected to 2, 1 is connected to 2, 2 is like, here we are telling about the graph, how the connections are, and we want how to, here we can write whatever we want, and g dot BFS. So where does this g existed? Like g is equals to graph. We are telling, hey computer, understand, we are just we are not using word graph. Instead we are telling, hey computer, g is equals to graph of everything whatever you done. So the graph is this one, the class that we created before and in the starting. So this is how this code works, and here is time complexity and auxiliary space. So this is about breadth first search. Thank you for listening. I hope you understand. Bye.